Good day, good evening, and welcome to today's webinar. My name is Mark Cox, and I am a Senior Communicator at INNIO. I'll be your host today. I'd like to welcome you to our webinar platform. You'll notice that this webinar is browser-based, so if you disconnect for any reason, please just click on the link that you received via email to rejoin the session. In order to ask questions, you can send them in via the Questions widget. Just type them into the box at the top left-hand corner of your screen and click Submit. We will allocate some time at the end of the session to address any questions or comments you may have. Please use the yellow Help widget if you require any assistance, and you can move, resize, and maximize any of the windows in front of you to get a better view of the slides. Now, please allow me to share a short presentation about our company, followed by today's webinar. At INNIO, we are moving energy forward with a focus on innovative gas engines technology. We develop, manufacture, monitor, and service fuel-flexible engines for power generation and compression solutions. Our Jenbacher business is specialized in power generation. INNIO's Jenbacher North American Sales and Service Hub is headquartered in Houston, Texas, and we have operations in Wisconsin, USA, as well as in Ontario, Canada, with INNIO's global headquarters and our core innovation center based in Austria. Out of our more than 3,500 global employees, more than 500 highly qualified INNIO engineers are focused on innovation. INNIO's Jenbacher business has more than 2,000 employees around the world. The first Jenbacher gas engine was manufactured in 1957. In total, Jenbacher's success builds on more than 90 years of engine experience. So far, from about 25,000 engines for power generation and CHP delivered worldwide, around 1,100 have been delivered to customers in North America. Today, INNIO runs manufacturing facilities with a total of 65,000 square meters, producing 5 product lines of high-tech engines with outputs from 200 kilowatts to as high as 10 megawatts. Our engines are known for overall efficiencies of 90% and more, their durability, fast start capabilities, and the ability to run on a broad range of fuels, including hydrogen. Jenbacher also offers a comprehensive set of lifecycle services. Jenbacher has always been a frontrunner in the gas engine industry. In addition to a series of world's firsts in technology, the business also has a history of growth in the United States and Canada. What started with a small sales and service office in Boston 30 years ago has grown into a large network of expert INNIO and distributor sales and service, warehousing, and logistics teams across North America. Jenbacher engines meet our North American customers' needs with top reliability and performance, delivering total efficiencies of up to 95% in cogeneration mode. We offer established, field-tested designs, optimized, robust engine components, along with a proven monitoring and control concept. Our engines can run on natural gas as well as a broad variety of renewable or waste gases. This makes them a great solution for reducing our customers' CO2 footprint. With the capacity to run on hydrogen, the potential to save even more emissions in the future is becoming reality. Our service organization provides everything you need to profitably run your Jenbacher power plant. You choose your tailored level of support, and INNIO will deliver everything from the digital myPlant asset performance management solution for optimized uptime and reduced lifecycle costs, all the way to remote operation, as well as fast on-site service support from our team of technicians. We also run a remanufacturing program for efficient overhauls and provide you with comprehensive conversion, modification, and upgrade packages to help you make the most of your Jenbacher engine. Let's look at a few of the most interesting Jenbacher solutions for North America. Most Jenbacher power plants run in combined heat and power mode and use up to 40% less primary energy compared to conventional generation of heat and power. We offer innovative microgrid solutions for a stable 24/7 power and heat supply, even if cities face a blackout. With our innovative greenhouse solutions, we power and heat greenhouses and grow houses while cleaning the exhaust gas for use as fertilizer, which promotes plant growth. Jenbacher-powered data center power plants deliver lower emissions along with fast start capability based on reliable pipeline fuel operation. Using renewable wastewater gas in Jenbacher engines can provide 100% of a sewage plant's energy needs and in the long run, achieve significant cost savings. We are ready for H2. Jenbacher's products are prepared for a CO2 neutral world and can support you with engines ready to run on hydrogen today. When you choose Jenbacher engines, you decide for a greener and more profitable future. INNIO, changing the world with better energy.
Yes, and a warm welcome to today's webinar on hydrogen engines as a net zero technology for North America. I myself am Christian Mueller, a Senior Sales Manager at North America here, based out of Houston, and I'll guide you through the first couple slides as an introduction, followed by Klaus Peierhuber, Strategic Product Development. We'll talk about hydrogen applications and some of the references we have. And then last but not least, Matthias Feldmann, our engineering platform leader for e-fuels, who will talk about the hydrogen engine development and testing. With that, let's go to the first couple slides. You already heard in the video a little bit about INNIO. INNIO Jenbacher is a leading energy solutions and service provider that empowers industries and communities with sustainable energy choices. As part of the INNIO brand, we have Jenbacher and Waukesha engine families, as well as our digital platform, the myPlant solution. We offer power generation solutions anywhere from 250 kilowatts to over 10 megawatts, as well as compression with the Waukesha brand, and thereby helping industries generate and manage energy sustainably while managing and navigating this fast-changing landscape of energy. We are headquartered in Jenbach, Austria. That's where our Jenbacher engines are built. And we also have operations here in North America, in Waukesha, Wisconsin, as well as Welland, Ontario, and myself here in Houston, Texas. A little bit about our company as far as it relates to our footprint. So obviously we have over the decades supplied engines to a wide variety of countries and in a wide variety of applications, including CHP, tri-generation, data centers, greenhouses, different biogas solutions, sewage and landfill gas, as you see on these little green dots here covering the globe where our engines are operating. And then highlighted here are certain installations which run on hydrogen fuels, be it 100% hydrogen or blends of hydrogen. So we already have a footprint there as well. Overall, we have delivered over 25,000 engines, which equates to 37 gigawatts. Many of these have been installed in Europe, as well as other regions. And we also have a very good footprint on the renewable gas side, as many of our engines do run on biogas, sewage, or landfill gas. And obviously with hydrogen, we're continuing that as a green fuel. 12,000 of our engines are digitally connected to myPlant. And that is growing as well as customers see the benefit of that digital solution. About North America now, obviously the energy transformation is going on here as our customers try to reduce CO2 emissions, as well as navigate the volatility, which is involved with additional renewable power generation. And one of the legislative measures which was put into place is the Inflation Reduction Act to help support that with different hydrogen incentives. So there is now available a clean hydrogen production tax credit or an investment tax credit, which incentivizes green hydrogen production or low carbon hydrogen production. So depending on the carbon intensity of the hydrogen production, a tax credit of up to $3 per kilogram of hydrogen can be gained, as you see on the table on the right side. So this really incentivizes low carbon hydrogen production. And it's expected that this could push hydrogen levelized production cost below the $1 mark per kilogram by the end of the decade. This tax credit is available for the first 10 years of operation for plants which are operational before 2033. Apart from this Inflation Reduction Act, obviously we realize that government decisions on energy framework and policies will drive a lot of these clean energy projects. Those are framed by the challenges of grid stability with retiring coal plants and the increase in renewables, as well as limitations on power transmission and distribution networks. So we think hydrogen could play a key role here, offering a solution to decarbonize peaking and backup power to support the grid, as well as providing a means of long-term energy storage. So overall, with that being said, green hydrogen is expected to play a key element in the US decarbonization efforts, as it provides a carbon neutral solution for energy and industrial sectors. So with that introduction, I will now hand it over to Klaus.
Thank you very much, Christian. And I'm continuing with the question, why do we need hydrogen? Actually, hydrogen, we need it for energy storage. There are a lot of storage technologies around, but when it comes to large amount of energy storage over a longer time, then we need molecules, and here hydrogen comes into play. We did an example on electricity storage in Germany for 20 gigawatts over 2 days, just 48 hours. This results in about 1 terawatt hour of electricity storage. And we ultimately end up with hydrogen being the solution. It can also be ammonia or methanol, but hydrogen is the basic solution. Here's a little bit more on the next slide, what we looked at in the energy production in 2017. In October 2017, there was a sudden change in the availability of renewables, and the dispatchable power plants from coal and gas had to ramp up quickly, provide 20 gigawatts within few hours, and this at least over 2 days, over 48 hours. This can be longer, this can be 1 week, this can be 2 weeks. And this 2 days and 1 terawatt hour of electricity storage or electricity demand, if we compare that with electricity storage from batteries, that would require a huge amount of batteries. A battery lasts about 4 hours. So we need a lot of parallel packages of batteries. Actually, we need 12 times 20 gigawatt batteries. And that ends up with a huge investment cost of about 48 billion euros. Compared to a gas power plant, it can be a big combined cycle, but also distributed power plants. If we estimate 800 euros per kilowatt of capex, we end up with about 16 billion euros investment cost. So this is a 1 to 30 difference, yeah? And that's why we need gas power plants to do this balancing of renewables and not batteries for long-term balancing over many hours, days, and weeks. So ultimately, where is the hydrogen coming from? There's hydrogen storage and transport on a technical level. It can be tanks, but this only for smaller amounts. Ultimately, we need a hydrogen infrastructure with hydrogen pipelines, hydrogen distribution network, and of course, hydrogen storage, large hydrogen storage, and this is typically underground hydrogen storage. We think hydrogen hubs and clusters will emerge first before these hubs and clusters will connect to a bigger interconnected hydrogen network, similar to the gas network what we have today. So where do we see our first applications with gas engines, with distributed power that could run on hydrogen instead of gas? We see data center of a very attractive application for hydrogen engines replacing diesel backup, because those data centers are typically running on on diesel, which is expensive, and running just in backup mode. And here we would replace diesel with hydrogen, which is more expensive, but also runs just in a backup mode. Other applications could be hydrogen from industrial use, or hydrogen that is available in hydrogen hubs, in microgrids or islands. Before we use hydrogen in bigger power plants for balancing renewables and CHP, larger CHP plants, we need definitely a hydrogen infrastructure and hydrogen supplied by pipelines. So when we look to our installed base on a global base, about 45% of our engines running already on renewable gases, mostly biogas. 55% is the remaining run on pipeline gas or natural gas. And this 55% of engine need to be converted to renewable gas over the next decades until 2050. So there will be some biomethane and hydrogen and also raw biogas. We will continue with that. Depending on the application, biomethane could be a better fit or hydrogen is a better fit. Let me show you our experience on hydrogen over the last 25 years with high hydrogen fuels. We have done several projects at in total about 250 megawatts with syngas and process gases containing high hydrogen content in 90 projects over 28 countries. And on the left-hand side, you see an example from Austria, where we installed 4 engines about 25 years ago, containing 15 to 17 volumes% of hydrogen. But when we look to the fuel, about 95% what is in this fuel is hydrogen and burns is hydrogen. The rest is typically nitrogen. All these engines have achieved 200,000 operating hours. So we have really long-term experience burning hydrogen. In the middle, we see a syngas application with about 30 to 40 volumes% of hydrogen that is coming out of waste gasification in this case. And on the right-hand side, we see a hydrogen admixing to pipeline gas, which I will show you in the next slide a little bit more. And then ultimately now we're going to 100% hydrogen applications. The project in Argentina, where we're mixing hydrogen up to 42 volume% is a very interesting one. It started about 15 years ago in an area where we have installed a lot of engines for the oil and gas production. And here, one of our customers installed a small wind park with 6.3 megawatts, as well as an electrolyzer with 0.8 megawatt. And then they produce hydrogen and store it underground in an empty gas field. They use this hydrogen to blend it to the natural gas for the gas engine when there is not enough wind available. And they do blending up to 42 volume%. The engine is in operation since 15 years and has achieved more than 100,000 operating hours. On this picture, you can see where the engine is installed. On the very left-hand side, you see the engine container, the 420 engine with 1.4 megawatt output. In the middle, you see the electrolyzer. And then in the back side, you see the oxygen compressor, because that is a byproduct from the electrolyzer operation. This project is from 2020, where we demonstrated a first field conversion from natural gas to hydrogen operation in Germany. It was done in Hamburg at the customer site, where we have installed a 1 megawatt engine that is a CHP engine with very high total efficiency, over 93%. And this engine was converted in the field from natural gas to 100% hydrogen operation. We did some tests with 20% hydrogen blending and then at 100% hydrogen operation. What we changed on the engine can be seen here on the bottom right. We changed the fuel system to a port injection system requiring 8 bar hydrogen pressure. We installed a cylinder selective combustion control system, and we installed a wastegate on the turbocharger. What was very interesting to see, and from our side expected, was lower NOx emissions when running on 100% hydrogen. We could reduce NOx from 250 milligram per cubic meter to less than 100 milligram when operating on 100% hydrogen. Now I'm coming to a project list that are more recent, that are projects and are for 100% hydrogen operation. This is a project where in South Korea for Hoesung in Ulsan, where we provided an engine with 1 megawatt, it's a 420 engine, to run on 100% pipeline gas as well as on 100% hydrogen. It's a CHP unit that produces steam, and the hydrogen is coming as a byproduct from the polypropylene production at the Hoesung chemical industry plant. So as I said, the engine is also producing steam for processes in the polypropylene production. The engine was delivered in 2023, this year, and will go in operation very soon. Our next project, which is very exciting, and I'd also already talked about data center. This is a real data center project where North Sea data center operator installed a new data center at Eindhoven in the Netherlands, and they selected hydrogen engines instead of diesel backup. They have other data center where they installed already a hydrogen fuel cell, and they have in total 15 locations, 15 data centers, and all these data centers should be decarbonized and running on clean backup fuel until 2030. They changed their design from diesel backup to hydrogen backup system with minor adaptations in the balance of plant, like a new PS system or the cooling system. And they selected 4620 that can run also on natural gas as a backup fuel, because the hydrogen is supplied in tanks and is stored in tanks, and this tank lasts for about 1 or 2 hours of hydrogen operation. If the electricity interruption is longer, then they can switch to natural gas. Another project in Serbia, this customer is installing and investing in a solar plant in the south of Serbia. And here they have problems with the feed-in of a 12 megawatt solar PV plant because the grid is not strong enough. So they install a small storage plant and also install an electrolyzer system to produce hydrogen. Then this customer, as this customer is in the business of CNG and LNG fuel stations, they transport this hydrogen to north, about 200 kilometers to north of Belgrade, where they install or invest in a fast charging station. And at this fast charging station, this customer has another challenge to get enough electricity out of the grid for the charging station. And that's why they install a 420 1.3 megawatt CHP engine to produce local power, and the heat can be sold to a nearby commercial building. We did some calculations on the economics, how this project could be a viable project. And we estimated 60 euros per megawatt hour for the cost of electricity from PV. Then we produce hydrogen. So the cost of hydrogen we estimate to be, due to efficiency, double. That means 120 euros per megawatt hour. 120 euros per megawatt hour is 4 euros per kilogram. And then we have to consider some capex for the electrolyzer as well as for the storage. So we estimate that the cost of hydrogen at 8 euros per kilogram at the site of production. Hydrogen will be then transported, and then at the CHP plant, the hydrogen is converted back to power and heat. And here we estimate, or we are starting with 240 euros per megawatt hour, so the 8 euros per kilogram. due to efficiency and heat bonus, we come up with 480 euros per megawatt hour for the electricity cost. And then we estimate this customer is selling electricity at 600 euros per megawatt hour. 600 euros per megawatt hour at the fast charging station means that about 20 charging can be done 20 times, or the 20 cars can be charged with 50 kilowatt hour. And for every charge, if they pay 30 euros, that means 30 euros for 50 kilowatt hours or for 300 kilometers, plus for 300 kilometers. And that is a typical price what people pay at a fast charging station. So 600 euros per megawatt hour of electricity sounds expensive, but in this case, it works out. This is another project, was our most recent project in Austria, where this customer is developing a hydrogen underground storage, converting a natural gas storage to a hydrogen storage, and producing locally hydrogen from overcapacity of solar and wind, storing underground, and in wintertime, they use a pipeline to take out the hydrogen, bring it to a CHP plant, and convert it back to power and heat. Because in the wintertime in this area, we have a lack of renewable energies from wind and solar. We have to run gas power plants. And here, this small plant can be replaced or can replace gas by hydrogen. This is a demonstration which is first of its kind in Europe, and we think it's a global first of its kind. So there's also a project in the US, a very interesting one, with gasification of waste, organic waste gasification, producing a syngas with 55 to 65% hydrogen. And then this hydrogen, or this syngas, is upgraded to pure hydrogen, to very clean hydrogen of 5.0 quality for the transport sector. And due to this upgrade process, there is a tail gas, and this tail gas will be mixed to landfill gas. And then this mixture is used in 3 420 gas engines. The plant is containing about 10% of hydrogen. This project is in California, and under the California law of carbon fuel standards, the hydrogen that is sold for transportation achieves a negative carbon intensity credit. So a very interesting project in the US. And with this project, I'm coming to a quick outlook. We have built the largest CHP plant in Europe with 20 gas engines just about 5 years ago. And this power plant produces 190 megawatt of electric power and 192 megawatts of thermal heat for district heating in northern Germany. It is a very flexible plant that can start very quickly and operates at high efficiency of more than 90%. It replaced a 50-year-old coal plant, and by that reduced CO2 emissions by 70% at this site. But in less than 5 years operation, the customer announced to convert this gas power plant to a hydrogen plant until 2035. And then it will be used for pure balancing of renewable power. And we work together with this customer to convert the engines from natural gas operation to hydrogen operation, latest until 2035. So with this outlook in projects, I'm handing over to Matthias, who will talk a little bit more about what ready for hydrogen means for our engines.
Yeah, thank you, Klaus, and very welcome to all of you also from my side. I will talk a little bit about our product validation work and activities that are ongoing here at our Jenbach headquarters related to hydrogen. Before I get started on the slides, just a quick reminder to the audience, you have the opportunity to already post your questions in the widget that is associated with the questions. So just type your questions in there, and submit them so that we can take care of them at the end of the presentation. So let's take a look at ready for H2, and let's start with the slide here that I'm particularly proud of because we have been working with the team here in Jenbacher and the engineering team and also our partner TÜV Süd here in order to achieve a concept certificate with respect to H2 readiness. So what does that mean? This concept certificate here, which is based on a guideline that has been developed by TÜV Süd, has been the foundation to basically check the technology that we have developed for our Type 4 and also for our Type 6 engines to run on 100% hydrogen. We have been audited in many areas from the engine core, the engine functionality control system, but also all the way into the plant end user documentation and in all related aspects to 100% H2 operation. And we received these certificates, being the first engine manufacturer for this particular concept certificate, and based on that guideline developed by TÜV Süd. And we're very happy that now we can also show this to you and pass this on to our customers to provide security on what does it actually mean in terms of H2 readiness, what's the definition, what's behind it. Here we have a third-party certificate that gives security for 100% H2 operation on new products, as well as on retrofitted products from our product line here coming out of Jenbacher for Type 4 and Type 6 engines. So we're really proud that we have achieved this great milestone. Looking at some more details here now, ready for hydrogen, what does it mean? What does it mean for us? There's two aspects really that need to be considered. One is 25% by volume H2 admixing in the pipeline gas. And then in contrast, we also have 100% H2 operation, which allows CO2-free operation of the engine. What we have developed at Jenbacher here is 25% admixing for our whole product line. We'll take a look at that in just a second to also see what it takes to retrofit existing units to operate on 25% H2. And with our Type 4 platform, we also offer 100% H2 operation, also retrofittable to the units that are already out there to basically buy natural gas operation today if you don't have H2 available yet, but have the security that you will not end up with a stranded asset as you can upgrade to 25% or 100% H2 operation in the future. So a few technical slides here talking about the physical properties of hydrogen and how they impact the fuel quality. The two left-hand charts are basically a base natural gas for different methane number, the different colors. And on the x-axis, we go from 0 to 20 or 30% H2 being added to the fuel. And you can see how with the addition of hydrogen and the increasing concentration, the physical property of the fuel mixture, the resulting fuel mixture is changing. Obviously, hydrogen has a very low methane number, in fact, has a methane number of 0. So as we add hydrogen to the fuel composition, the methane number of the fuel is reducing. If we take a look at 20% admixing, we typically see a 10 to 15 reduction in the methane number. Heating value is also being reduced. Hydrogen has a superior gravimetric heating value, but on an volumetric basis, because of its very low density, the heating value is actually fairly low. And therefore, as we add hydrogen to the natural gas stream, we also have a situation where the lower heating value of the fuel is being reduced. And that can have some implications, some consequences to the layout of your gas train that is delivering the mixture to the engine. If you do an upgrade there, for instance, or if you install a new engine running on up to 20 or 25% H2, it needs to be made sure that the volumetric flow rate can be handled by the gas train. On the far right now, looking at the CO2 CO2 reduction potential as we add H2 to the natural gas as a base fuel. Here now we're taking a look at the whole range from 0 to 100%. And what's worth noting is that this is not a linear relationship. So 20% addition of H2 on a volumetric basis is not a 20% CO2 reduction. It enables you to about 7 to 8% of CO2 reduction as you go to 20 to 25% H2 added to the natural gas as a base fuel. And so we can see that this admixing technology is a first appropriate step in CO2 reductions, but to really reduce CO2 emissions from our gas gensets or gas engines, we need to thrive for high concentrations in hydrogen, ideally for 100%, because obviously then we have emitted all of the carbon in the fuel, and therefore we will also not see any CO2 emissions in the exhaust. So as we talked a little bit about these categories, I'd like to elaborate a little bit from our product line perspective, how we think in these different categories and how the engines might differ based on these categories. In general, we think of three categories, A, B, C. You can see them labeled at the very top. On the very left, we see an engine category where natural gas and H2 is delivered to the genset via the gas grid. So completely done, pre-mixed H2 and natural gas is being delivered by the utility company, by the gas network company to the genset. And in this case, we have two subcategories that we need to think of. One is, and they both depend on the H2 concentration in the fuel gas. Up to 5%, any of our natural gas gensets can handle a mixture of hydrogen natural gas. So if you don't expect more than 5% by volume of H2 in this natural gas, then you don't need any further modifications of the genset. You can continue operating the genset because at this low concentration, H2 is not really impacting the engine performance, and also we're not in need of any modifications to the genset. You just can keep running, basically. For the range of 5 to 25% by volume of H2 being added to the fuel, now the physical properties of H2 become significant. And so here we have a hydrogen blending kit, basically, that's available. We need a sensor that tells us what is the H2 concentration, can also be an external input, but we need to know what the H2 concentration in the fuel is. And then we can adapt via software the engine operating points to make sure that the engine is operating as it's supposed to be on mixtures up to 25% H2. Category B, now if we look at that, we have also two subcategories here, B1 and B2. Now we're looking at hydrogen concentrations of up to 60% by volume for category B1, or 100% even for the case of category B2. For category B1, up to 60%, we're still applying a pre-mixed system. So we're adding the hydrogen and natural gas mixture right after the air filter via a gas mixing, gas dosing system, feeding it through the entire air system to the engine. We run or we utilize gensets here that we have vast experience with from our special gas line. So leveraging our experience with syngas engines, for example, wood gas engines that have high H2 concentrations in the fuel by default. These technologies we're leveraging in this area and can achieve up to 60% H2 in this pre-mixed fashion. B2, now we're talking about up to 100% H2 operation with the opportunity to also run lower H2 concentrations or pure natural gas. In this case, we have an additional fuel system fitted to the engine. Klaus already mentioned the port fuel injection system. We'll take a closer look at that, what that means, but this is really required to safely operate the engine at concentrations above 60% and all the way up to 100%, which then is category C, where we have solely the port fuel injection system and can run on pure hydrogen up to 100%. For these two last categories, B2 and C, For our Type 4 engine, we have a product available that is available to you on a special release right now, and can be purchased from us for operation in the field. Here's the same slide, just a little bit of a different wrap-up, summarizing. Here you can see all of our platforms on the left-hand side of the graph, from Type 2 all the way up to Type 9 engines with the respective power band in 60 Hertz operation in natural gas, which is indicated by the gray bars. And then you can see the categories A, B, C, as I just explained them to you. So you can see for the entire product range, we have the capability to run up to 25% H2 being admixed to the natural gas. The category B with up to 60% is available for our product lines 2, 3, and 6, with the product line 4, Type 4 engines being able to run all the way up to 100% hydrogen as a fuel. And you can also see for category C, the expected release dates for the remaining platforms to offer solutions that can run on 100% hydrogen. Type 6 is the next platform that we're focusing here, with a release date anticipated for 2025. And then Type 9, Type 3, and Type 2 will follow subsequently. So what to expect as we talk about this, or what's the engines that we're talking about here in a little bit more detail, specifically focusing on Type 4, 6, and 9 engines. So you can see Type 4, we can handle power plants with an output from 1 to 20 megawatts on H2. Type 6 being a larger engine now enables us to go from 40 to 60 megawatts of a power plant, as we have a typical output here of about 3.5 megawatts. And then our very large engine, Type 9 engine, with expected 9 megawatt of output on H2, would then be for really large power plants with a 50 to 200 megawatt power output. All of these have fast start capability, and specifically for Type 4, you already saw from Klaus that we are actually utilizing this in a data center application for backup power. Let's take a closer look briefly here at the 25% admixing, and what are the key features for this category. Quick overview: if you weren't to do anything to the engine control system as we add hydrogen to the fuel, you would basically go for your burn rate from the orange graph to the blue graph. So because hydrogen is a rapidly combusting fuel, you see that the combustion that is taking place in the engine is getting much faster. And if you don't do anything, that means high peak pressure, so high stress on the engine, high NOx emission, and high NOx emissions. And these needs to be corrected. And therefore, we utilize, as I said, an H2 sensor system and software compensation package. And we can add or we can modify the key parameters of the engine so that as independent of the H2 concentration up to 25%, we maintain NOx emissions, and we also maintain the peak firing pressure in the same limit or even lower compared to natural gas operation. So key here is we need to know what's the concentration of H2 and the software package. How did we develop this? Here's an aerial image of our company. You can see in the yellow in the green outline our INNIO company. And in the past, we have been trucking in hydrogen via trailer to feed our test beds into the development. But I'm very pleased to announce that in the future, we will actually be connected to a pipeline, our very own pipeline that is, as we have teamed up with TIVAC, a local utility company that is operating the Aachensee Kraftwerk, a hydropower plant, which is located in the top left-hand corner of the picture. There we will be generating hydrogen via electrolysis from water power, and then also store it in a compressed tank in the gaseous phase. And the orange line is actually indicating the pipeline that then is feeding the hydrogen to our facility, and will be able to run here independent of trailer logistics on green hydrogen from hydropower. This is a rendering of the facility. You can see on the right-hand side in administrative building. In the middle section is the electrolyzers that are being set up, and on the far left behind the walls, which are for fire protection measures, is the storage facility. And in the front, we also have an opportunity to either load or unload trailers, and also an H2 fueling station. This is some background information on the setup of this plant. We're looking in our initial stage here of the total capacity of 2 megawatt electric for H2 production. This gives us about 35 kilograms per hour of H2 stream, which then we can feed into the storage tank, which has a total capacity of 1 metric ton. And from there, we can feed at a rate of about in excess of 100 kilograms per hour to our facility and feed our test beds in order to do the development work. Obviously, with this setup, our cost for hydrogen is also decreasing, as we no longer have the advanced logistics of trucking it in, and this can be produced from a green source here with the power plants, the hydropower plant. So a clear advantage for us here in Jenbach to do the development with green hydrogen. Now let me complete the presentation here with an outlook in category B and C to complete the picture. For category B, I think Klaus has mentioned the vast amount of projects that we're doing, like Chico, for example, with the 40% H2 admixing in Argentina, which has been in operation since 2008. And we have many more plants that are up and running, various plants. A few that I would like to pick out here is the Hanseberg Natur, which you can see on the right-hand corner, is located in Hamburg. Also mentioned by Klaus, being the first demo engine here for our Type 4 on 100%. And Hyoseong Korea has also been mentioned by Klaus, which is also Type 4 engine on 100%. So let's take a look at the remaining categories B2 and C, which is the 100% engine operation on H2. Here, specific focus on our Type 4 engine, which has been released for the 12 to 20 cylinder count here, ranging from 635 kilowatts of electric output to above 1 megawatt electric power output. A rule of thumb here that's pretty interesting is that you can calculate about 80 kilograms of H2 consumption per megawatt of electric power output, which is also represented in the data set for our J420 engine. Now, let's take a quick look at the key of this technology. I mentioned to you that we are utilizing a port fuel injection system. And in this video, you see on the left-hand side, the conventional system that we're using, where we are mixing the pipeline gas and air right after the air filter, and we feed it through the entire air system. Then combusting it in the engine, and we're emitting obviously then CO2, water vapor, etc. On the right-hand side now, because hydrogen is such a reactive fuel, we want to minimize the amount or the volume that we have of H2 and air mixture present in the engine. And therefore, we have introduced a port fuel injection system, which allows us to dose the hydrogen just in front of the combustion chamber, just in front of the cylinder head, which gives us the ability to greatly reduce the mixture of H2 and air in the engine. And also an advantage is here that we can, on a cylinder selective basis, correct the amount of fuel per cylinder individually, also leveraging the pressure-based control that we have on our hydrogen engines. And we have very good transient performance because we can very quickly adjust the fuel ratio if we need to pick up or shed power in an island mode application. Here's a side-by-side picture from our first prototype in Hamburg. On the left, you can see the conventional layout with the pre-mixed air and fuel. And on the right-hand side in yellow, the bright yellow color, you can see the H2 rail that is providing the 100% H2 via the port injection valves on a cylinder individual basis to the engine. And also you can see the ignition rail that has grown significantly, because now this also needs to house the port fuel injection driver, the cylinder pressure-based control system next to the ignition system on this ignition rail to safely operate the engine. With that, my part is over. I'll hand it back to Klaus for a quick wrap up, and then we're ready to take any questions. Thank you very much.
Thank you, Matthias. Yeah, I have 2 more slides to conclude. The first slide is showing our product development based on a Type 6 engine, what we did over the last 30 years. And when you look at this chart, you can see a significant power and efficiency increase. Actually, we now can produce with the same Type 6 cylinder 2.5 times the output than 30 years ago. And at the same time, we increased efficiency from 33 to 47%. A similar development path we will do for the hydrogen engines. Today we are at the starting point. We already have developed hydrogen engines and have engines that can run on 100% hydrogen and also on natural gas and hydrogen. But going forward, we will invest much more and increase performance, increase power and efficiency to similar levels than what we can achieve with natural gas operation today. And finally, at the beginning, we said, why we're doing hydrogen, why we need hydrogen for power generation. It is all about renewable energy, electricity storage, seasonal storage, storage over a long period in large amounts. And here the way goes through hydrogen. Produce hydrogen out of renewable power, overcapacity or over excess of renewable power from wind and solar, do large hydrogen storage, typically underground, and use it later in centralized, ideally in decentralized power plants, ideally in CHP power plants. So hydrogen production in the summertime, hydrogen electricity for reconverting hydrogen to electricity in the wintertime. And we think it is essential to look at efficiency and use CHP power plants in the wintertime, because then we not need only electricity, we also can use the heat for district heating. And then we can take out more than 90% of the hydrogen producing power and heat for cities, microgrids, hubs, and so on. But as explained at the beginning, a hydrogen infrastructure with an interconnected hydrogen grid will be essential. Not necessarily at the beginning, but longer term, it will be essential. And with that, we are at the end. This is what we had today. We thank you very much for your attention. And I think we have a couple minutes left for some questions.
Yes, that's right. This is Mark again. I'd like to thank Klaus, Matthias, and Christian for the presentation this evening. We'll get in some questions and answers in just a moment. But before we do that, I'd like to remind you that you can still ask some questions. Please type them into the system using the questions widget. We'll do our best to get back to you tonight. Although we do have quite a few questions, I'm not sure we'll be able to answer everything live. Those that we don't get to live, we'll get back to you via email. In addition to that, there'll be a very short survey at the very end of the webinar. We'd appreciate it if you take a few seconds and just give us some feedback on our efforts tonight. It helps us to get better. And don't forget that this presentation will be available via stream at the same place that you logged in to join us this evening. It'll be online for a year. So we hope that you'll enjoy it again. If there was any parts that you missed or anything you'd like to see again, please make sure to take advantage of that stream. Let's get into some questions. And the first question will be, I believe this would be best for Matthias. It's a question about the stability of H2, of hydrogen. Is there any risk of explosion on land during storage or transportation? Matthias, is that one for you?
Yeah, I can take that. I guess in general, for any of the fuels that we combust in our engines, gaseous fuels that is, whether it's been natural gas or biogas, landfill gas. They're all combustible, so they all have a certain hazard or risk associated to them with respect to fire and explosion. For hydrogen, it's a little bit specific, or maybe, I don't want to say more dangerous. If you apply the appropriate rules and follow the guidelines, it's just a fuel like any other ones. But what makes it a little bit more sensitive here is that you typically have a very low ignition energy and a very wide ignition window. So it's a very reactive fuel that can easily be ignited. Therefore, specific precautions must be taken. One of them is the port fuel injection system, for instance, that we have introduced to our engines. But also, if you think of your plant, you need to make sure that the plant is appropriately set up to handle H2 in a safe way. If you follow the standards and rules there, then I believe hydrogen is not any more dangerous than any of the other fuels that we have.
Excellent. Thanks, Matthias. Perhaps this is one for you, Klaus. The question is, what purity of hydrogen do you require? Are there any stream contaminants that you need to be aware of?
It's a good question, because that typically comes up when we look to use hydrogen in fuel cells. We are using hydrogen in a combustion engine, and here the engine is not sensitive from hydrogen purity. That's why we can use the tail gas at the American project in California, and we don't need the high purity of 3.0 or the 5.0.
Great, thank you, Klaus. I believe this is another one for Matthias. A bit of a technical one. How does Jenbacher set up an engine to run on H2 or natural gas? How does the engine know which fuel it's running? And how does the engine management adjust? What parameters need to be adjusted between the two fuel types?
Yeah, very good question. I've been elaborating around the port fuel injection system. So for our dual fuel setup, what we have here is we have the port fuel injection system that handles the H2 that has been added to the engine, but we have not removed the natural gas fuel system, which is the low pressure mixing system that is adding the fuel right after the air filter, sorry. Now that gives us the ability to control two streams of fuel on the engine independently from each other. So we know by the methods of our control what the fuel mixture is, if we're running solely on natural gas, solely on hydrogen, or any mixture in between. And we can use that information along with the information we get from our cylinder pressure-based controls to adapt parameters like spark timing, air-to-fuel ratio, various positions like wastegate position, etc., to optimize engine operation on the plant that we're on.
Okay, excellent. So let's see. Here's a good question. The ready for H2 engine is rich burn or lean burn? Klaus, would you like to answer that one?
Lean burn. And I mentioned on one project that we can reduce NOx emissions when running on hydrogen, 100% hydrogen, compared to 100% natural gas. And that is because we're running with more air, we're running with a higher lambda, more excess air than on natural gas. That reduces the NOx emissions.
Okay, excellent. I think here's a couple of questions that are quite similar, Matthias. The first part is about what upgrades are needed to burn 100% hydrogen. And the second one, which I think is very much in the same line, is how does the addition of hydrogen and ultimately going to 100% hydrogen affect maintenance and maintenance cost, including oil, lube oil?
Mm-hmm. Yeah, a good question. So as we talk about modifications, maybe that first. Port fuel injection system has been named. That's a key for any hydrogen concentration above 60%. That's roughly the number. If you want to go above that, we need the port fuel injection system. Along with the port fuel injection system, we also introduced the cylinder pressure-based controls, because those two go hand in hand and complement each other very well, and enable us to keep the performance of the genset high and secure operation and output of the engine. So those are the key things that need to be added. Obviously, on the plant side, gas train needs to be for 100% H2 ready also. And we have a line of special hydrogen oils that can be used, which are there to enhance engine performance and also lifetime of the components when on hydrogen operation. In total, if we take a look at the total cost of ownership and maintenance cost, with these added technologies, we're going up compared to natural gas, but still in a reasonable way, given the CO2 emissions that we're reducing.
Excellent. Thank you, Matthias. I see that we've reached the end of our allocated time for tonight's webinar. I'd like to once again thank Matthias, Klaus, and Christian for the great presentations. Please make sure to complete the brief survey I mentioned earlier. We really appreciate your interest in INNIO Jenbacher, our hydrogen products and our services, and we hope you've enjoyed and learned something from our webinar this evening. And we thank you for your time.
Thank you.
Thank you.
Thank you.